Welcome. In this video, we'll talk about using logarithms to help us with differentiation. We start by just reviewing some basic concepts that we've already learned. First, the natural logarithm has a simple derivative. If I have the logarithm of x, its derivative is 1 over x. And that's defined for the domain of the logarithm, which is when x is greater than 0. In addition, we learned that if I take the logarithm of the absolute value of x, that has the same derivative of 1 over x, but this time it's true for all x except 0. If I use composition of functions, I get a generalized rule. So here, if I let u be any expression, could be any formula at all, the derivative of the logarithm of u will be 1 over u times the chain rule factor du dx. Now this is only going to be true when u is greater than 0 because the domain of the logarithm required that our input was positive. Well, that's not very useful if I might have a negative value for my expression. If I happen to have the logarithm of the absolute value of u, its derivative will be 1 over u times the derivative of u. And this will be true as long as u is not equal 0. We'll be using these principles to be able to help us with other differentiation problems in this video. Once we know how to find the derivative of the logarithm of an expression, we can use that to help us calculate a number of problems. Now, one thing that we need to be aware of is that there are many instances where we benefit from rewriting the input of our derivative before we use the operation itself. For logarithms, we have 3 rules. That a logarithm can be rewritten when I have a product, when I have a quotient, and when I have a power. So we're going to illustrate how to use those properties in order to calculate a derivative of a logarithm where that formula inside the logarithm is expressed as a product. So what we want to do is start by thinking about how does this expand. So my logarithm inside is, I've got an absolute value of a product, and so the first thing we're going to do is rewrite it with the absolute value on each factor separately. Because if I have a product and take its absolute value, it'll be the same as the absolute value of each factor multiplied together. So my original formula will be equal to the logarithm of each factor. So I have the absolute value of x raised to the 4th, the absolute value of 2x plus 1 raised to the 3rd, and the absolute value of x squared minus 5 raised to the minus 5. Once I've rewritten my formula as the logarithm of a product, I can use the logarithm's product rule to rewrite that as a sum of the logarithm of each factor. So let's write that down. I now have the logarithm of the first factor plus the logarithm of the second factor plus the logarithm of the third factor. Each of these terms, notice, are written as a formula raised to a power. So I can use the power rule to bring the power out as a constant factor. At this point, my function is written as a sum of a constant times a logarithm plus a constant times a logarithm plus a constant times a logarithm. I'm ready to take a derivative because these are now, each term is a simple formula. Let's name our function. We'll call this function f of x, so that we can calculate the derivative and have a meaningful equation. The derivative, f prime of x, equals the sum of the derivatives of each term. My first term is 4 ln absolute value x, and so its derivative is the constant 4. Derivative of a logarithm is 1 over x. Second term is a constant 3. The logarithm's derivative will be 1 over its input times the derivative of its input. And the third term, I've got a constant negative 5. The derivative of the logarithm is 1 over its input, x squared minus 5, times chain rule factor, the derivative of its input is 2x. All I have left is simplifying, and I get my derivative is 4 over x. 3 times 2 gives me 6, so I get 6 over 2x plus 1. And the third term, I get minus 10x over x squared minus 5. And this formula is the derivative of the expression I started. Now that we've learned how to use the properties of logarithms to make it easier to calculate the derivative of logarithms, we can use this to help us find derivatives of other expressions. When I have a function that's written in terms of products, quotients, or powers, it's often convenient to use logarithms to help me in my calculation of the derivative. We have 4 steps. To differentiate a function, we're going to start by creating a new function, the logarithm of the absolute value. And then we're going to use 2 methods to find the derivative. We always know that the derivative of the logarithm is equal to the inside derivative f prime over f. That's the chain rule. And so if I multiply by f of x to the other side, I find out that my derivative of my unknown f prime will always equal the original function times the derivative of the logarithm of absolute value of my function. What we're going to do is we're going to take the logarithm of the absolute value, expand it using the rules, and then take its derivative to find f prime of x. Let's look at an example on how this would work. I want to find the derivative of a formula that involves multiple steps here. I've got a quotient, I've got a product, and each of these terms has a power. I could try to find the derivative using ordinary rules, the quotient rule, the chain rule, and the power rule, but we want to see how the logarithm can help us find it in a more direct way. Let's call this inside function my f of x. And I find it convenient to often look at the denominator factors and think of them all as having negative exponents. So let me rewrite that with the negative power. My original function f of x, I can't do anything else to rewrite that. But if I put it in a logarithm and create a new function, the logarithm of the absolute value of f of x, then I can rewrite this using the properties of logarithms, this new formula, as a sum of 3 terms. Each factor gets its own term, and the power gets multiplied out front. Now that I've rewritten the logarithm of the absolute value of f of x as a sum of terms, each of these terms individually will be fairly straightforward to calculate, and I'll be able to find the derivative. Okay. So we have our function. We've calculated an expanded version of the logarithm of the absolute value of my function, and we're now ready to calculate the derivative. The derivative of the logarithm of the absolute value of a formula is always equal to the derivative of the formula divided by the original formula. On the right-hand side, we've rewritten the logarithm of the absolute value of f as the sum of 3 terms. And so we can write the derivative as the sum of the individual derivatives. So I get the first term, I get a constant of 4, 1 over the input, 1 over 2x plus 1, times the derivative of its input, 2. The second term I get a constant of 3, 1 over x squared minus 3 is the derivative times the derivative of the inside, 2x. And the third term I get minus 2 times 1 over x squared plus 1 times 2x. Let's simplify the right-hand side. I get 8 over 2x plus 1 plus 6x over x squared minus 3, and then minus 4x over x squared plus 1. Our goal was to find f prime, the original function's derivative. And on my left-hand side, notice I have f prime of x over f of x. So my f prime, my derivative I wanted, equals the original formula, f of x, times the derivative I've just found. And so I'll rewrite my function as the original formula, that's f of x, times, it's a group, the derivative we found of the logarithm. So 8 over 2x plus 1 plus 6x over x squared minus 3 minus 4x over x squared plus 1. And this is the derivative that I wanted to find.